to look at the effect of changing container volume and what that does to an equilibrium position. So we're going to consider the reaction dinitrogen tetroxide decomposing to nitrogen dioxide. First, we start off with a system that is at equilibrium. After equilibrium is reached, the container volume is decreased. Will the moles of nitrogen dioxide increase or decrease or remain the same? Justify your answer. So let's take a look at what happened for the gases. So we see that all of the pressures increase. The system is going to shift to reduce the pressure by shifting in the direction that minimizes the moles of gas. So remember, by Le Chatelier's system, Le Chatelier's principle, the system will always try to undo the change. Since we've increased the pressure, the system is going to shift to reduce the pressure. It will do that by shifting in the direction that minimizes the moles of gas. So if we look, we see that the NO2 decreases much more rapidly than the N2O4 decreases. And that's because we have more moles of gas on this side of the equation, on the product side. So our answer, without even looking at this graph, you should be able to say the moles of nitrogen dioxide will decrease. The system will shift to reduce pressure by reducing the moles of gas. The reaction shifts to make more N2O4 because there are fewer moles of gas on the reactant side. So let's try another one where we don't have a graph that is telling you what's going on. Consider the reaction nitrogen reacting with 3 moles of fluorine to make nitrogen trifluoride. The container volume is increased. Will the moles of NF3 increase, decrease, or remain the same? Justify your answer. So what we have now is we have more volume, which means the pressure has dropped, which means that the system is going to try to get back to its initial pressure. It will do that by going to the side of the reaction that has the most moles of gas. The system will shift to increase pressure by going towards the side, or going to the, in this case, it's going to the reactants to produce more moles of gas. So a consequence of changing the volume is that the pressure changes, and then you have to undo the pressure change. And we need to answer the question, thus the moles of N3 and F3 will decrease, because we are going to shift to the side of the equation that has more moles of gas. All right, let's go ahead and just keep going on changing temperature. Consider the following system in an equilibrium at 258 K. Will the concentration of NH3 increase, decrease, or remain the same if we increase the temperature to 301 K? Justify your answer. So here's our reaction. N2 plus H2 makes 2NH3, and we're told that our delta H of reaction is negative 91.8 kilojoules per mole. This is exothermic. Heat is produced. Okay, so I could add plus heat here because heat is going to be made. And then I can think of this, is heat a product or is it a reactant? Now, one of the things about changing the heat is if we change the temperature, the rates of the forward and reverse reaction change, because remember K, little k, the kinetic K depends on temperature. There I've got the rate equation for you. So changing temperature is the only change that alters K. All right, so we're going to rewrite the reaction showing heat energy as a product or reactant. So we have N2 gas plus 3H2 gas is in equilibrium with 2NH3 gas, and because it is exothermic, we're going to say that heat is a product. Heat is produced. Anytime you add heat, the reaction is going to shift to absorb the added heat. Since the reaction is exothermic, the reaction shifts in the reverse direction and the NH3 concentration decreases. Notice that the value of K also is going to decrease. Let's try another one. Consider the reaction. CO2 plus H2 gas is in equilibrium with H2O gas plus carbon monoxide. This time we're told delta H of reaction is 31 kilojoules per mole. Predict what will happen to the concentration of CO2 if the temperature is reduced. Justify your answer. So I'm going to rewrite this equation, and I'm going to include heat on either the product or the reactant side. In this case, I've got positive 31, so this is an endothermic reaction, which means that I'm going to add the 31 kilojoules over here. So I'm reducing the temperature, so I am removing heat, which means that the reaction is going to shift in this direction to replace heat. The reaction shifts to replace the lost heat. Since delta H is positive, the reaction shifts towards reactants. And then I have to make my claim. So I have explained what happens. Since delta H is positive, the reaction shifts towards reactants. The concentration of CO2 increases. Okay, so we are going to stop there